dengan aman. Jadi, tidak ada limbah radiasi yang mencemari alam karena selalu dipantau oleh Batan.
Jadi, kesimpulannya, setiap hal adalah kebaikan jika digunakan dengan takaran dan kebutuhan yang sesuai. Begitu juga dengan energi nuklir.
Berarti nggak ada yang perlu dikhawatirkan dong ya dengan tenaga nuklir. Nah, gimana nih teman-teman? Udah makin paham kan sama radiasi nuklir? Nah, sekarang Kak Egy punya pertanyaan nih buat teman-teman. Yang pertama, bagaimana ciri tanaman yang sudah terradiasi nuklir? Yang pertama, dia menjadi tahan hama. Atau yang kedua, dia menjadi cepat layu. Ayo yang mana ayo? Ya.
Okay. Well, ladies and gentlemen, thank you for joining our webinar. We will commence shortly. Well, okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning. I wish you everyone a pleasant morning and serenity. Welcome to the expert talks on radioisotopes, radiopharmaceuticals, and biodosimetry research and development held by Research Center for Radioisotopes, Radiopharmaceuticals, and Biodosimetry Technology, National Research and Innovation Agency of Indonesia. Today, there will be a talk entitled Design and Development of Molecular Probes for Theranostic Applications. I am Ilma Drajatin. I will serve as the webinar's host today. Okay, please wait a moment. Okay, I'm going to continue. I'm Ilma Drajatin. I will serve as the webinar's host today. It is an honor to me to inform you that among us here, we have distinguished head of Research Center for Radioisotopes, Radiopharmaceuticals, and Biodosimetry Technology, National Research and Innovation Agency of Indonesia, Dr. Tita Puspitasari, MSE. Distinguished guest speaker, Professor Kazuma Ogawa, an expert of Radiopharmaceutical Institute of Medical, Pharmaceutical Health Sciences, Kanazawa University, and our respected moderator, Dr. Phil Rasnadini Haryuni M-Farm. Well, ladies and gentlemen, please allow me first to read the agenda for today. The first agenda is the opening session. The second will be the webinar session led by our moderator. And last but not least, there will also be a closing session. Okay, ladies and gentlemen, please allow me to read the webinar's rule of conduct. To all attendees, please mute your Zoom meeting, as attendees are expected not to interrupt the speaker's presentation. If you have any questions, please type ASK, then proceed with your name, followed by your institution and a brief question in the chat box. You may also ask questions by activating the raise hand feature on the Zoom meeting until the moderator invites you to. Due to the time constraints, the moderator will present only selected questions to the speaker during the discussion session. If you wish to fill out the attendance list, please visit the link that will later be embedded in the chat box. Okay, ladies and gentlemen, we are now in the opening session. Without further ado, I would like to invite on Dr. Tita Puspitasari, MSE, Head of Research Center for Radioisotopes, Radiopharmaceutical, and Biodosimetry Technology BRIN, for some welcoming and opening remarks. Ibu Tita Puspitasari, the time is now yours.
Okay, thank you, Dr. Ilma, the future Dr. Ilma. Good morning, distinguished guest speaker from the Kanazawa University, Professor Kazuma Ogawa, ladies and gentlemen. First of all, as head of the Research Center for Radioisotope, Radiopharmaceutical, and Biodosimetry Technology, Research Organization for Nuclear Energy, I would like to welcome all of you to our webinar series, namely Expert Talk, in this field of radioisotope, radiopharmaceutical, and biodosimetry. This is a second expert talk in this year. As already mentioned in the flyer, our topic today is design and development of molecular probes for theranostic application. As we know, the needs of radiopharmaceutical worldwide for diagnostic and therapy are increasing from year to year, which has implication for the need of improving the research development activities in this field. So we hope that by sharing knowledge, cooperation and collaboration among us, activities in this field can be accelerated. Last but not least, we do hope that today's expert talk can benefit all of us. Thank you for the committee for preparing this webinar and all participants for your willingness to take part in this webinar. And please enjoy this talk. Yeah, thank you.
Okay, thank you. We would like to express our gratitude to Dr. Tita Puspita Surya MSc for the welcoming and opening remarks. Well, ladies and gentlemen, before we begin to our main agenda, now we will be taking pictures together. So please, sir and madam, activate the camera and video function on your Zoom application. I would like to invite the IT team to assist in taking pictures. Please be prepared. I'm going to count from 1 to 3. Okay, again, please turn on the camera video on your Zoom meeting. I'm going to start counting to take the pictures. Okay, ready? Okay, everyone, 1, 2, 3. Please wait a moment and hold in your pose while our AT teams are taking our pictures. Okay, I think we finished taking pictures. Thank you for your cooperation. Well, ladies and gentlemen, we have now reached our main agenda, the webinar session. All presentation and discussion will be presided over by Dr. Phil Ratnadini Haryuni M.Pharm. First, allow me to read her brief biography. Well, Dr. Phil Ratnadini Haryuni is a researcher at Research Center for Radioisotopes, Radiopharmaceuticals, and Biodosimetry Technology BRIN. She has extensive experience in radiopharmaceuticals and molecular biology, particularly in relation to cancer cell biology research, cellular mechanisms, and antibody-based radiopharmaceuticals. While she has also published several scientific articles on these subjects in some international journals, Mrs. Ratna holds a Bachelor of Biology degree from 11 Maret University, as well as a Master of Pharmacy degree from the University of Indonesia. She completed her doctoral studies in pharmaceutical sciences at the University of Toyama, Japan, and also attended the postdoctoral program at the Department of Neurology at the University of Toyama, Japan, which she completed in early 2022. Ladies and gentlemen, let's welcome our moderator, Mrs. Ratna.
Oke. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Ratna, and I'm your moderator today. Ogawa sensei, okoe wa kikoemasu ka?
Hai.
Hai. Ohayo gozaimasu, Ogawa sensei.
Ohayou gozaimasu.
Hajimemashite. Watashi no namae wa Ratna desu. Yoroshiku onegai shimasu.
Yoroshiku onegai shimasu.
Hai. So before we start our seminar today, let me introduce our guest speaker. He is Professor Kazuma Ogawa, or we call Ogawa Sensei. He received his PhD from Kyoto University, and then he started his career in 2002 at Kyoto Prefectural University of Medicine. Then he continued to the Kanazawa University at the Athens Science Research Center in 2004, and 2007 Athens Research Center of Kanazawa University, and 2009 became assistant professor at Clinical and Analytical Sciences Kanazawa University, 2015 associate professor at Clinical and Analytical Science Kanazawa University, and 2019 become professor until now at Clinical and Analytical Sciences Kanazawa University. He has a lot of specialties and skill expertise. His specialties are radiation science, laboratory medicine, physical pharmacy, radiochemistry, nuclear chemistry, and medical chemistry. His skill expertise are bone, rhenium, PET, apoptosis, nuclear imaging, radionuclide imaging, molecular imaging, and diagnostic imaging. And today he will present and share his experience at design and development of molecular probe of theranostic application. Before that, I would like to explain that this presentation will be divided into two segments. First is presentation from Ogawa Sensei about 45 minutes, then continue with a discussion about 1 hour. So, 始めましょう。じゃあ、先生、よろしくお願いします。
Thank you for kind introduction. Can I talk 40 minutes, 50 minutes? I don't know exact time.
そう、時間は45分ぐらい、プレゼンテーション。はい。
OK。
で、次は、question and answer。1時間ぐらい。
Okay, can I share my slide?
Yes, time is yours.
Okay. Can you see my slide?
Yes, Sensei.
I have no COI with regard to the presentation. Can you see my today's talk, the slide? Okay.
Yes.
Okay. At first, I will talk about concept of radio theranostics. At first, I introduce myself. I'm Kazuma Ogawa and 50 years old. I was born in Shizuoka. Probably you don't know the city. I will show you the location in the next slide. I like beer and baseball and clothes. There are my clothes and this is my son. And do you know Kyoto? As I was introduced, I graduated Kyoto University, and after that, I was an assistant professor in Kyoto Prefecture University and moved to Kanazawa. Kanazawa is located around here, and Shizuoka is here, and Kyoto is here. And I belonged to MD Anderson Cancer Center from 2010 to 2009. MD Anderson is located in Houston, Texas. I would like to start my presentation about research. I think you know the word of Theranostics. Theranostics is a synthesized word of therapeutics and diagnostics. It means agents or techniques that couple diagnostic imaging and targeted therapy. The word has been frequently used in last 10 years, especially in oncology. I entered the word of Theranostics in PubMed yesterday. How many papers did I find? The results were more than 110,000 on very many papers. Moreover, about 90% of the result was from 2013. The result by year have been growing like this. Meanwhile, the word of radiotheranostics has been used in recent years. Radiotheranostics means theranostics with radionuclides. Namely, it means combination of molecular imaging with targeted radionuclide therapy. By diagnostics and therapeutic radiopharmaceuticals with similar biodistribution for imaging and therapy, respectively. And the therapeutics radiation dose can be calculated using time activity curve from imaging data like this. Namely, we can expect therapeutic effects and side effects from imaging data before therapy, so we can select patients and optimize the injection dose correctly. Therefore, radiotheranostics can contribute to personalized medicine. How is PubMed search for radiotheranostics? I also entered the world of radiotheranostics yesterday. The result of this research were only 107. It has been also growing, but number is too small. I would like to contribute increasing the number of this. Radionuclides with similar chemical characters can be introduced into same site like this. For example, same color elements on the periodic table could be introduced into same creator or same position in compound. For example, halogen elements can be introduced on benzene. If diagnostic radionuclide and therapeutic radionuclide can be introduced into same precursor, and both compounds are stable, both compounds could show similar biodistribution. It is very important for radiotheranostics. As I said, the word of radiotheranostics has been used in recent years. However, the concept of radiotheranostics has been used for a long time in clinical nuclear medicine. Classically, iodine-131 therapy for thyroid cancer is one of the radiotheranostics. This slide and next slide show good examples of radiotheranostics in clinical. As you know, radio-labeled octreotide analogs are famous for radiotheranostics. This figure shows the combination of gallium DOTATOC PET imaging and lutetium DOTATOC for radionuclide therapy. In Japan, octreotide scan using indium-111 for SPECT imaging and lutathera for lutetium therapy were approved and used. MIBG has been used for radiotheranostics combined with iodine-123 imaging and iodine-131 therapy using same compound, like this slide. Iodine-131 MIBG coupled with iodine-123 MIBG was approved in Japan in 2021. Targeted alpha therapy has gathered much attention by excellent therapeutic effects of actinium PSMA therapy, like this. I think you saw the images many times in some conferences. Probably, I think I saw more than 50 times in conferences. But supply of actinium-225 is not enough in the world, especially in Japan. Meanwhile, astatine-211 is one of alpha emitter radionuclides, and astatine-211 can be produced by domestic cyclotron in Japan. Astatine is located below iodine on periodic table here. Because it is one of halogen elements, astatine has some similar chemical properties to other halogens. Thus, radiotheranostics combined between astatine-211 alpha therapy and iodine-123 SPECT imaging could be possible. Decay scheme of astatine 211 is shown here. There are 5 cyclotron facilities to produce astatine 211 in Japan. Previously, I got astatine 211 from Osaka University. Sometimes I did experiments in Osaka University, and sometimes in delivered astatine from Osaka University to Kanazawa University. It takes about 4 hours by car. Now I got astatine 211 from Fukushima Medical University. I deliver astatine 211 from Fukushima to Kanazawa like this by car. It takes at least 6 hours. Because I was tired after delivery of astatine 211, after that, my students do experiments overnight. Fukushima Medical University has cyclotron MP30. The middle-size MP30 can accelerate proton, deuteraton, and alpha particle. The proton beam is accelerates as negative ion, and beam energy can charge from 15 to 30 mega electron volt with 100 microampere current. Deuteron beam is also accelerates as negative ion, and beam energy can be changed from 8 to 15 mega electron volt with 50 microampere current. Alpha particle beam is extracted through an electrolytic detector at fixed energy, 32 mega electron volt, which is optimized for astatine 211 production. Irradiation energy of alpha particle is optimized in detail using energy degrader or aluminum foil. Beam is transported to vertical irradiation target system that accommodates target materials in different forms and shapes. An automatic target transport system provides safe handling of the target after irradiation, and resolution station located on the irradiation loop allows the transfer of irradiated targets to the hot cell as a solution. I introduced the basic research about NAAT. As you know, iodine-131 NAI has been used for therapy of thyroid cancer. It is a certain version of NAI. This study was performed by Dr. Watabe at Osaka University. Based on these excellent therapeutic effects, first in human clinical trials of NAAT started from 2021 in Osaka University. Next, I introduce MABG. It is a certain version for MIBG. Dr. Oshima at QST Takasaki performed therapeutic study of MABG in tumor-bearing mice. The mouse picture shows the tumor condition at 21 days after MABG therapy. In this dose, the tumor almost disappeared. The pictures and the figure show excellent therapeutic effects of MABG. First in human clinical trials of MABG started from 2022 in Fukushima Medical University. Probably, you know RG peptide. RG peptide has high affinity for alpha V beta 3 integrin, and the integrin is a marker of angiogenesis and is expressed on some kinds of cancer cells. Therefore, RG peptides has been used as carriers to cancer in nuclear medicine. Peptides are promising carrier. to cancel for astatine, I think. Because the half-life of astatine 211 is 72 hours. It is too short for big molecules, such as antibody. However, there were few reports about astatine-labeled peptides. Moreover, there is no report about astatine-labeled RC peptides when I started this research. Then I selected RC peptides as a model peptide. I tried to synthesize RGD peptide, astatine-labeled RGD peptides, and evaluated usefulness of radiotheranostics by combination between radioiodine and astatine-labeled RGD peptides. At first, I prepared radioiodine-labeled RGD peptide by classical chlamyl T method. Biodistribution of this compound is shown here. It shows high accumulation in tumor and low accumulation in all other tissues except for excretion tissues such as kidney and intestine. Thus, I tried astatine labeling using same condition as iodine labeling, but astatine labeled reaction did not proceed. Some papers also reported that astatine labeling with antibody was impossible using this method. So I gave up astatine labeling using this method. Meanwhile, I reported that astatine label can be performed by a standard halogenation reaction using corresponding precursor containing tributylstanyl group. Thus, as a preliminary study for astatine labeling, this compound was prepared according to this scheme. The result of biodistribution experiments of this compound was shown here. In this figure, the scale of y-axis is different from here. Contrary to my expectation, these compounds show extremely high accumulation in intestine, like this, and low accumulation in tumor. For this tumor, y-axis is here, so tumor accumulation about 2 grams. I suppose that the higher lipophilicity of the compound in previous slide might cause its unfavorable biodistribution. Then I designed and synthesized this compound with ethylene glycol chain as a hydrophilic linker. As a result of biodistribution experiments of this compound, accumulation of radioactivity in the intestine was decreased compared to the compound without linker. However, accumulation in tumor was not enough. So I supposed that another approach was necessary to introduce radiohalogen to phenylalanine in cyclic RGD-FK. I designed this labeling precursor with tributylstanyl group. To synthesize this compound, I synthesized FMOC-D for iodophenylalanine as a material for solid phase synthesis. After synthesizing the peptide by general solid phase peptide synthesis method, cyclization and deprotection was performed. So this non-radioactive iodine peptide was prepared. Meanwhile, tributylstanyl group was introduced into here, this reaction, and radio iodination and deep protection was performed. By in vitro integrin binding assay, affinity of this compound for alpha V beta 3 integrin was evaluated. This result indicates that introduction of iodine molecule did not hinder the affinity of RGD peptide for alpha V beta 3 integrin. For astatine labeling, tin-astatine exchange reaction was performed like this. After that, the protecting protected group was performed. After purification, astatine labeled RG peptide. After purification, astatine labeled compound was obtained. However, radiochemical yields was not good, and it takes a little long time. So, to modify the yields and synthesis time for astatine labeling, after the protection, the butyrylstyrene group was introduced like this. And after that, astatine labeling was performed. As a result, yield, radiochemical yield, and synthesis time were improved. At this time, astatine labeled compound was determined by HPLC. Astatine has no stable isotopes, so I compare the detention time astatine labeled compound with non-radioactive iodine labeled compound. And double tracer biodistribution experiments of these peptides were performed in tumor-bearing mice. As you can see, both labeled peptides show high accumulation in tumor and very similar biodistribution pattern. As I explained, this similar biodistribution is very important for radiotheranostics. Moreover, the tumor accumulation was significantly decreased by co-injection of excess amount of RGD peptide. Namely, the tumor accumulation was specific to alpha V beta 3 integrin. I will summarize this topic. Astatine labeled RGD peptide and iodine labeled RGD peptide were prepared by synthesis of this precursor. These radio-labeled RGD peptides show similar biodistribution and RGD and alpha V beta 3 integrin specific tumor accumulation. The results indicate that radiotheranostics by combination between spectroimaging with iodine 123 labeled RG peptide and targeted cell therapy with astatine 211 labeled RG peptide could be useful. As it is known that dimerization of RGD peptides increased its affinity for alpha V beta 3 integrin, I designed, synthesized, and evaluated this compound as next step. Called non-radioactive iodine-induced dimapeptide was synthesized according to this scheme, and radioiodine and astatine 211 labeled dimapeptide was synthesized according to this scheme. It was not easy, and radiochemical is not high. I prepared monomer RGD peptide and dimer RGD peptide with iodine and without iodine. and evaluated the affinity of these compounds for alpha V beta 3 integrin. As a result, both dimer peptide increase the binding affinity for integrin, as I expected. In biodistribution study in tumor-bearing mice, iodine level dimer RG peptides show higher accumulation in tumor, as I expected. Next, therapeutic experiment with iodine 131 labeling this peptide was performed. However, tumor growth was not significant compared to control group, non-treatment control group. Previously, Dr. Yoshimoto and I reported a therapeutic study of yttrium-labeled RGD peptide. Single injection of this dose of yttrium-labeled RGD peptides show similar result like this. Thus, in this case, radiation dose to tumor tissue may not be enough. I wanted the therapeutic experiment using astatine 211. However, in this time, therapeutic study of astatine labeled this peptide was not performed because radiochemical yields were not enough and separate radioactivity of astatine 211 at this time was small. So I decided to go next study. Generally, combination patterns of radionuclides for radiotheranostics are limited. Because only radionuclides with similar chemical property can be introduced into same precursor, as I explained. Here, I hypothesized probes for radiotheranostics combined with multi-radionuclides such as gallium-68 for PET imaging and astatine 211 for alpha therapy will have useful clinical applications. For this purpose, I designed these compounds, which contain both a halogen element introduction site and a metal complex site in one molecule. Non-radioactive iodine gallium into this compound was synthesized according to this scheme, and gallium labeled compound was prepared according to this scheme and determined by HPLC, and iodine labeled compound was according to this scheme and determined by HPLC, and astatine labeled compound with non-radioactive gallium was prepared according to scheme and determined by HPLC. And in this time also, I compared the detention time. I compared detention time between astatine labeled compound and iodine, non-radioactive iodine introduced compound. I synthesized these compounds, and integrin binding assay was performed. As a result, introduction of daughter ligand and gallium daughter complex did not affect the affinity for alpha V beta 3 integrin. In therapeutic study, as I expected, gallium-labeled compound and iodine-labeled compound with same chemical structure showed equivalent uptake. Meanwhile, contrary to my expectation, cellular uptake of compound without gallium, this radioiodine-labeled compound, was lower than that of the compound with gallium, like this. Reflecting the cell uptake study, the compound without gallium showed lower uptake in tumor than compound with gallium in biodistribution experiment in tumor-bearing mice. On the other hand, gallium-labeled compound and iodine-labeled compound with same chemical structure showed almost same biodistribution pattern, especially at 1 hour post-injection. SPECT-CT images of gallium-labeled compound was performed. As you can see, this compound clearly visualized the tumor tissue. Next, I evaluated astatine-labeled compound in cell uptake study. The astatine-labeled compound showed same degree of cellular uptake as that of iodine-labeled compound. And the uptake was inhibited by co-incubation of excess amount of RGD peptide, like this. In biodistribution experiments, astatine-labeled compound and iodine-labeled compound showed similar biodistribution pattern. I will summarize this topic. The similar biodistribution pattern among gallium-labeled compound and iodine-labeled compound and astatine-labeled compound indicate that radiosynapsis where gallium-68 for PET imaging is combined with astatine-11 for alpha therapy should be applicable using a molecular design with 2 labeling sites for radiometal and radiohalogen. Therefore, radiotheranostics with multi-radionuclides could contribute to personalized medicine and thus provide significant benefits to patients in the future. Next, for higher accumulation in the tumor and higher therapeutic effects of astatine-labeled RGD peptide, I synthesized new astatine-labeled compound. But this study is undergoing, so I cannot show the exact structure of this compound because this data has not been published. X means black box. But in the therapeutic experiments, the tumor growth was significantly inhibited by single injection of this astatine-labeled RGD peptide of this dose, at this dose. It is very good result. Therefore, this compound is promising for targeted alpha therapy. Next, I will talk about sigma receptor ligands. Sigma receptor plays important role in functional and pathological changes, especially in brain. And 2 subtypes, sigma and sigma 2, has been identified. Moreover, sigma receptors have been reported to be overexpressed in various cancer cells. So sigma receptors may be promising target molecules for cancer imaging and cancer therapy. Pentarosine is known as a sigma-1 selective ligand, and haloperidol is known as non-selective sigma receptors ligand. I used this compound, resamicol, as a lead compound for sigma receptor ligand. In this slide, I show the chemical structures and affinity of besamicol and its analogs for sigma receptors. Previously, we have developed several besamicol analogs as sigma receptor ligands, introduced iodine into the benzene ring. Besamicol analogs have enantiomers. As you can see, plus enantiomers showed higher affinity than minus enantiomers. And in these iodine besamicol analogs, this plus PIP showed the highest affinities for sigma receptors. So I prepared radioiodinated PIV and evaluated the compound using cancer cells and tumor-bearing mice. As a result of biodistribution experiments of this compound in tumor-bearing mice, presented in here on the next slide, PIV showed much higher uptake and long tension of radioactivity in the tumor compared with each radioactivity level in blood and muscle. Therefore, tumor blood and tumor mass uptake ratios are very high, while a low level of radioactivity in the stomach indicates that deiodination does not occur. However, as you can see in this slide, radioactivity levels in the liver and the kidney and other tissues are high. Also, the levels of radioactivity decrease gradually. The clearance was slow. I performed the therapeutic experiments using iodine 131 labeled PIV, because plus PIV showed long detention in tumor in biodistribution experiments. I show the result in this slide. As you can see, tumor growth in the mouse treated with iodine 133 PIV was significantly inhibited compared to that of untreated control group. Next, I tried to synthesize astatine to 11 labeled besamicol analog instead of iodine. PATB shows similar biodistribution as PIV. This result indicates that radioceranostic between PIV and PATB may be possible. However, in this time, the amount of supply astatine 211 was not enough to perform therapeutic experiments, and accumulation of radioactivity in non-target tissue was high, so I did not perform therapeutic experiments using astatine level compound. Next, I aimed to develop other sigma receptor ligands by changing piperidine ring of besamicol to piperidine ring and introducing alkali carbon chains of different lengths from 0 to 4. In these compounds, C3NV, N equals 3 compound, has the highest affinity for sigma receptors. I introduced iodine at para position to C3NV, and its affinity for sigma receptors was evaluated. And iodine label this compound was prepared and its biodistribution was evaluated. As a result, tumor to non-target tissue ratios were improved compared to PIV, like this. I introduced iodine into paraposition in previous study on benzene because PIV has the highest affinity for sigma receptors. However, for this compound, I don't know whether paraposition is best or not. Thus, I synthesized this compound with bromine at different position instead of iodine. Because I also reported there is little difference between iodine compounds and corresponding bromine compounds. Little different means affinity is little different. And bromine compounds were inexpensive as starting materials. Moreover, Dr. Shiver, one of my colleagues, reported that the exchange of cyclohexanol to cyclopentanol improved the selectivity to sigma-1 receptor. Thus, I also synthesized derivatives with cyclopentanol. The table shows the result of affinity of synthesized bromine compounds for sigma receptors. Among these compounds, compound 11 is sigma-1 selective ligands, and compound 12 showed high affinity for both sigma-1 and sigma-2 receptors. Thus, I decided to focus on these compounds and evaluate them in the iodine form. Iodine-introduced compounds were synthesized and their affinity were evaluated. These iodine compounds show similar affinity to the corresponding bromine compounds. Based on this result, radioiodine label compounds were synthesized and evaluated in vivo. I show the result of biodistribution experiments. Iodine 125 labeled MIC2N5V and MIC3N5V. Both compounds showed high accumulation of radioactivity in tumor, and the radioactivity in non-target tissue was reduced compared with previous compounds. It's good result, especially at 20 hours. Tumor to non-target tissue ratio was so high. Comparing two compounds, this compound and this compound. MIC2N5V showed lower accumulation in non-target tissue, while MIC3N5V showed high detention in tumor. So I cannot decide which is better for radionuclide therapy. Besides, based on good result of biodistribution experiments of radioiodine labeled compounds, I prepared astatine labeled compounds and evaluated their therapeutic effects. As a result, these astatine labeled compounds significantly inhibited tumor growth in tumor-bearing mice compared to non-treated control group. This is the last topic of my talk. At first, I introduced Dr. Suzuki's study. He developed new scaffold for astatine labeling. This neopentylglycol as a scaffold for astatine labeling. It is known that benzoic acid structure is frequently used for iodine labeling, for protein labeling, and peptide labeling. However, certain labeled compounds with benzoic acid are often unstable. Dr. Suzuki synthesized these compounds and performed biodistribution experiments of them in normal mice. As a result, this compound, a certain level on this compound was decomposed and free astatine accumulate in stomach and thyroid. Meanwhile, this compound was stable and show similar biodistribution with corresponding iodine level compound. These results indicate that neopentyl glycol would be a useful scaffold for radiotheranostics between radioiodine and astatine. So I think, what about benzoic acid derivatives? Could structural modification of benzoic acid derivatives provide a more stable labeling moiety? So I started a new mice study. Previously, Scott Wilbur, a very famous researcher for astatine compounds, Scott Wilbur reported iodohypuric acid is stable in vivo, but astatinohypuric acid is unstable in vivo. So I put these compounds as difference compound. I designed, synthesized, and evaluated 3 kinds of hypuric acid derivative with different type of functional group into this. One of them, compound 10, showed very good stability in vivo. As you know, after deiodination and disastatination, free iodine and free astatine accumulate in stomach and thyroid. So these tissues are used as indexes for deiodination and deastatination in vivo. And I can not show the exact structure today of this compound B11, B10, C10. C6 is this astatine compounds unstable. However, I will inform you the exact structure and the data until the end of this year, hopefully. I performed my studies with my collaborators in Kansas University, my collaborator and my student in Kansas University, and at the beginning, I got astatine 211 from Osaka University, and now I got astatine from Fukushima Medical University. I thank my collaborators. Thank you for kind attention. Thank you.
Thank you, Ogawa Sensei. Well, that's all the presentation from Ogawa Sensei. Now we come to the next section, that is a question and answer. For the audience, if you have any question, you can raise your hand via Zoom and mention your name. There's some question also I saw in the chat block, but first, please, the audience, if you have any question, you can ask directly to the Ogawa Sensei. Is there any question? So while waiting, I will read from the chat box. First is from Isa, dear Ogawa Sensei. Is it safe to apply alpha therapy if the unspecific organ target is still have accumulation, such as in the intestine? じゃあどうぞよろしくお願いします、先生。
Sorry, I don't understand. First question of chat.
Yes. So it is safe to apply alpha therapy if the unspecific organ targets still have accumulation, such as in the intestine.
You mean accumulation of non-target tissue of alpha therapy is so dangerous?
So I will ask to Dr. Isa. Dr. Isa is here. You can ask directly.
Please repeat your question.
Yes, I mean the toxicity in the
Okay.
specific organ. Yeah.
Of course, toxicity in non-target tissue is very important. For example, actinium DOTATOC and actinium PSMA has high toxicity in kidney. However, toxicity is in intestine for excretion from liver to intestine to feces. It's not so high, I think, because radium for bone metastasis was extracted from intestine to feces, but not so high toxicity to intestine. So for some tissues, we take care toxicity for alpha therapy, but the toxicity is different for using beta particles, I think. Is it okay?
It's okay, Sensei. Arigatou gozaimasu.
Do you still have any question, Dr. Isa? If no, I will continue to the next question from Munir, dear Ogawa Sensei. What is the advantage of astatine MEBG and iodine MIBG? Is there any difference in the radio labeling method? So, dozo, yoroshiku onegaishimasu.
I would like to share my slide. This in basic research, MABG has much higher therapeutic effects to MABG. So now clinical studies is going. So some MD and researchers expect higher therapeutic effects in patients also. And I don't know exact labeling method, sorry, because I don't have experience for astatine labeling of MABG.
Okay. Is there any question from the audience? Okay. Okay, Pak Hendris, silakan.
Okay, thank you. Can you hear my voice?
Yes.
Yes.
Good day, Professor Ogawa. Thank you for sharing your research. So I have a question. We already know that the astatine can bind to carbon, boron, and nitrogen. So, and we also know that the binding between the astatine and carbon is quite unstable in vivo. And now people tend to use the binding or the design with boron. So do you have any plan to modify your compounds so it can bind to boron to make it more stable in vivo? So that's my first question. Thank you.
As you said, some researchers reported astatine bind to boron element, and they reported this bind is stable, as you said. But some researchers prefer astatine level with boron element. Of course, this strategy is good. However, I think astatine carbon bond is not usually unstable. Some compound, some astatine carbon bond is stable, but exact mechanism is not clear now. Mechanism means the astatination mechanism. So some researchers suggest that some enzyme related to the astatination, but we don't know. So I want to develop the new compound, and I clear the mechanism of deacetination. Sorry, I cannot say exact compound now, but I want to develop new compound and clear the mechanism of deacetination simultaneously. Okay.
Okay. Thank you. I have another question. Can I ask you? I can see you develop some sigma ligands, and most of them have bromine as their substitution. So what is the reason why you choose bromine, and do you consider to use another substitution to improve the selectivity or the affinity to the sigma 1 or sigma 2?
Sorry, please say it again.
Your sigma ligands, most of them have bromine substitution. So do you consider to use another substitution to improve the selectivity or affinity to the receptor? Maybe use like a methoxy or nitrile group as the substitution?
Some researchers used methoxy group and something. Not only bromine, some functional group is also could be used. You mean, for example, for carbon 11 labeling?
Yeah, probably. Yeah.
Some researchers perform like your strategy. I think it's one of good methods. I think it's possible. Not only iodine and bromine. We can some functional group instead of iodine, bromine. Affinity should be not to decrease so much.
Okay. Yeah, I also think that when we use different substitution, it could be a really strong synthetic or medicinal strategy to improve the finding. Thank you for your answer and discussion. Thank you, Bu Ratna.
Okay, thank you, Pak Hendris. Is there any question from audience? Maya-san, you want to say hi to your sensei? Hisashiburi da ne. じゃあ、どうぞ、よろしくお願いします。
Theranostic Sensei, how are you?
Good. Hi.
Sensei, this webinar held by my collaborator in Indonesia. Of course, they are your collaborator also because we already discussed. We will expand our collaboration with Japan, of course, which is Ogawa Sensei also. So hopefully, Ogawa Sensei, when will you come to Indonesia? Hopefully this year, we can visit this research center. Maybe in November, maybe. Hopefully.
I want to talk with Indonesian people directly.
Yeah, of course. Of course, as I said, I want you to come there to come to Indonesia to visit my university and also to visit this research center. But unfortunately, our island is different. I'm in Sulawesi Island and this research center in Java Island. So maybe this is close to, this is in Jakarta, I think. So when you first land to Indonesia, maybe we can go to first, this research center and then come to my university. Hopefully,
I hope so.
we can visit Indonesia this year, Sensei.
Yes, we're also waiting, Sensei, for collaboration.
Yeah.
University and the research center and also Kanazawa University.
Very good.
So
Yes.
Sensei Ogawa.
Butita.
Yeah, Sensei Ogawa, actually our previous head of the center is he was graduated from
Kanazawa.
and nowadays he become our chairman of research organization for nuclear energy. So we are very welcome for you to visit our institute.
Yeah, very good.
Okay.
Thank you, Butita, and thank you, Maya-san. And then, is there any question from audience?
I think somebody raised hand.
Diar. So please, time is yours.
Okay, thank you, the committee. Good morning, all participants and Sensei. My name is Diar from ITB. Okay, Sensei, I'm very interested to your complete research. I'm very interested to your data about therapeutic effect of your substance in tumor bearing, maybe. So I want to know why it's happened and how this phenomenon attract. Because in my opinion, the radiotherapy just say about something like biodistribution or something like that. So why the therapeutic effect is under this phenomenon? Okay, thank you.
I don't understand your question.
So please repeat your question more slowly.
Oh, okay. Okay.
Some noise contained.
Okay. Thank you, Sensei. About your therapeutic effect of your substance to tumor bearing.
Yes.
Why it's happened?
Mm.
Because I think it just say about biodistribution, but it's another data or another phenomenon. Why it's happened and how it's attract. I think it's clear.
What happened in tumor?
Okay, the therapeutic effect. The increase of therapeutic effect of your substance to tumor bearing in your last graphic.
I performed therapeutic experiments using tumor-bearing mice. I don't understand your question. What happened?
Okay.
Mungkin bisa disampaikan bahasa Indonesia dulu, nanti Mbak Ratna mungkin bisa bantu ya, maksudnya apa?
Oke.
Atau di kolom chat, karena ini agak sinyalnya agak ini ya, apa? Suaranya agak kurang jelas.
Oh, begitu ya.
Feedback
Oke.
Di mute kali ya. Nah. Okay, while waiting, they are typing the question. I will go to the next question from Herlan. Dear Ogawa Sensei, I just wonder about your black box compound. Can you share what the special feature for this novel compounds?
It's a special feature.
So can you share what the special feature for this novel compound?
Next page. Okay. That black box is actually containing protein albumin binder. Do you know albumin? Do you know albumin binder? That black box molecule binds protein in blood, especially albumin. Can you hear me?
Yes, Sensei.
And blood clearance was very slow, and tumor accumulation became high, and therapeutic effects was good. But I will publish paper in this year also. So you can
please
see
wait.
Please wait. You can see the result hopefully until the end of this year.
Okay, Sensei. So for Herlan, please wait until end of this year, so we will know what is the black box, what is the special feature from the black box. So be patient, please. Okay, this is the next question from previous audience from Dear. Dear Sensei, I just want to know how therapeutic effect of your substance, especially in tumor-bearing mice, could increase beside the increase of biodistribution? Because I think it's a different area. How about that question? Can I repeat the question? So she wants to know how the therapeutic effect of the substance or compound, especially in tumor-bearing mice, because she saw that it could increase beside the increase of biodistribution.
I don't understand the question exactly, but therapeutic effects correlates the accumulation in tumor because therapeutic effects is related to radiation dose to tumor tissue and tumor cells. So if tumor accumulation in biodistribution experiments increase, of course, therapeutic effects should be increased. Okay.
Yes, yes, I catch the answer, Sensei. So maybe this because the actinium, so from the radioisotope, maybe some people doesn't know exactly about the radioisotope and the effect on the therapy. So maybe this is the question: why she asked about the increase in the biodistribution. So how about the answer, dear? Is it clear for you? If no, you can type again in the chat box. Oh, okay. So next question from Ibu Titis. Dear Ogawa Sensei, interesting to talk from you. I think Ibu Titis here, so maybe you can ask directly to Ogawa Sensei. So Miss Titis, time is yours. Don't be shy. You can ask directly to Ogawa Sensei.
It is one question from chat.
Yes, but Titis is here, Sensei. So I ask to her to ask directly to Sensei. Still mute? Okay, Miss Titis.
Hello, Ogawa Sensei. Can you hear my voice?
Yes.
What feedback?
Interesting talk from you.
Thank you.
Astatin 211 has the same properties as halogen, so I guess astatin 211 is also volatile. As we know, it is easy to occur a contamination if we work with some volatile radioisotopes. I want to know, how do you set your working area up in your laboratory for your safety, since alpha particle emitters are very high risk? Thank you, Sensei.
You are right. Astatin became to gas easily like iodine, as you asked. It's right. So we should take care about contamination and especially alpha. As you know, alpha particles are dangerous for us. So, but it's same dealing with iodine. Iodine 125 and iodine 131, iodine 123. we should take care about dealing with iodine. I think it's of course more dangerous. Astatine is more dangerous, but astatine, the half-life of astatine is just 7 hours. So of course we should take care, but short half-life is good for good, not bad for contamination.
Okay, Ms. Titis, you still have question?
My answer is I don't have special equipment for astatine.
Thank you, Sensei.
Okay, thank you, Ms. Titis. Actually, Ms. Titis is one of our researcher here, and Sensei, she have planned to use alpha particle emitters, and we don't have experience before to using this alpha particle emitter. So that's why we asked to Ogawa Sensei, is there any like a special treatment or no to prohibit the contamination, or a special trick or something that Sensei can share with us?
But I think not the special for alpha particle emitter. Alpha particle emitter and other radionuclides maybe same for me. I understand your meaning, but I don't have special equipment and special experience about alpha emitter. Okay.
はい、わかりました。Is there any question from audience that want to directly ask to Ogawa Sensei? If no question, one question from me, Sensei.
Yes.
So I would like to know, Ibu Rin. I will give first the audience. So Ibu Rin, she's our researcher and collaborator with Maya-san. Maybe in the future, we'll intend with Ogawa Sensei to perform some experiments and collaboration. So Miss Rin, time is yours.
Thank you, Miss Ratna. Hello, Prof. Ogawa or Ogawa Sensei. It's really nice to have you here in our Zoom meeting. Actually, I'm the one who emailed you yesterday for this expert talk webinar. I'm actually the collaborators of Maya-san regarding the development of peptide-based radiopharmaceutical. Yeah, you may remember me from the email. So I emailed you yesterday. So regarding the, I have discussed with Maya-san regarding the development of PSMA radiopharmaceuticals, and we are interested in developing new PSMA legions. And as a newcomer of this PSMA-based radiopharmaceutical field, I would like to ask you whether you have some experiences or hints or suggestions to us to how to develop or design new PSMA legions. So we are, how to say, like the don't get lost in developing these new PSMA ligands, because we are really new. What we are doing now is only the radio labeling of lutetium with lutetium 177, and related to that, I also wonder whether you could offer us such a possibility to have some trainings in your research institute So probably I can join Maya-san to go to your research institute and have some trainings regarding the peptide synthesis and some others thing. Thank you very much, Ogawa Sensei. Thank you, Bu Ratna.
Hi, dozo sensei.
Yeah. I don't know your question. You mean you request the suggestion of design of PSMA ligand? You will design the deuterium level PSMA ligand, right?
Yes, so we are interested in developing new PSMA ligands, and we want to know your suggestions to how to say to start with this how to say the design of new PSMA ligands. So we are looking to your suggestions.
It is not easy. I also make some PSMA ligand. Now in nuclear medicine, PSMA is the most promising ligand, as you know, for imaging and therapy of breast cancer. So many researchers make PSMA ligands. So it is not easy to make new ligands. So I can't say some suggestion about the design. If I have an idea, I will do by myself. So how did you do about to make PSMA ligand?
We're not started that yet. Yeah, we just perform some radio labeling of PSMA with lutetium-177.
Okay. At first, you should make, for example, PSMA 617. It is not difficult to make the ligands. At first, you should synthesize some ligands, reported ligands, and after that, you should make your new ligands. It is not easy to make new ligands for PSMA, I think, because many researchers want to make good ligands in the world. Okay.
Okay, Ogawa Sensei. And another questions, in the future, perhaps there's some possibilities to have some trainings of research in your research institute. Is it possible? Because peptide synthesis is kind of new for us, so we want to go to your research institute and so have some trainings related to peptide synthesis. Is it possible to do?
Possible.
Arigato gozaimasu, Sensei Ogawa.
As I said last year, Sensei, I asked you that my friend, it is possible for my friend or for my collaborator from Indonesia to come to get training for peptide synthesis, and she is Miss Rin, Sensei. So if this year I can visit to Japan, maybe Miss Rin also will come to with me to Kanazawa University, Sensei. Is it possible, Sensei? Because she need like LOA to apply grant from Indonesia for this training. It is possible to for you to give her like LOA,
Okay.
letter of acceptance. Oh, yes. Mr. Congratulations. One from Ms. Atna, is it possible to give one question for Ogawa Sensei?
Okay.
Okay, thank you. Sensei, I want to ask you about nanoparticle. What do just like discussion, Sensei, what do you think about nanoparticle as a carrier for radionuclide or radionuclide or imaging agent? But we use nanoparticle as delivery system. I know you perform this experiment also in your laboratory, but I don't know how about the result. So if you don't mind, can you share to me or share to us about nanoparticle as a carrier for radionuclear medicine? Thank you, Sensei.
Thank you. About nanoparticle, what do you want to ask me about nanoparticle?
I mean the promising, for example, promising for
promising.
Yes, like promising for
Okay.
compared to only peptide as a carrier for radionuclide, or yes, I think you know what I mean.
I think nanoparticle is one of promising carrier in nuclear medicine, and now I combined nuclear medicine and other modality. So I use nanoparticle now in my lab, especially as assistant professor Munekane in my lab dealt with liposome and some nanoparticles. So I think nanoparticle is good candidate of carrier, candidate of carriers to cancer and cancer therapy. Okay.
Okay, about the kind of nanoparticle, can you tell to us which one is advantageous of the kind of nanoparticle, for example, AU or liposome?
Sensei, maybe the question is what kind of nanoparticle that become good candidate? Ogawa Sensei,
Yes.
聞こえますか? 聞こえますか?
Yes.
So maybe
I can hear you, but I cannot
hear Maya-san. So maybe I can repeat her question. So what kind of nanoparticle that a good candidate for this?
Now I use liposome and nanodroplet. Do you know? I use, but some kinds of nanoparticles should be good candidates. Not one kind. My associate professor deals with gold nanoparticle. So many researchers deal with many kinds of nanoparticles. I think I cannot select one candidate.
Okay, how about the answer, Maya-san?
Thank you, Sensei. Thank you.
Okay.
Okay.
Sorry, my connection is not is unstable.
大丈夫です。Is there any question from the audience? Because we still have time. So while waiting, maybe I will continue a question from me, Sensei. Because I'm biology and molecular, so I want to ask, in the astatine labeled with RGD peptide or iodine labeled RGD peptide, what mechanism that cause the cancer cell, tumor cell become died? So what a mechanism, for example, apoptosis or other? So could you explain, Sensei?
Exact mechanism is not clear. Generally, alpha particle break double standard of DNA. So after that, cancer cell will die. But some researchers suggest immune system of in cancer tissues is important. So not only DNA damage is important to kill tumor cells and tumor tissues. I think it is not clear now. Generally, alpha particle break double standard of DNA, but I think not only.
So it's mean the alpha particle break the double-stranded DNA, so no need for this compound to enter inside the cell. I mean, like internalization.
Of course, if DNA damage is important, the location of alpha particle emitter is important. Close to DNA is better, but outside of cells, if there is outside of cells, alpha particle emitters exist out of cells, but alpha emitter can alpha particle can go to DNA. For example, radium accumulate in bone, not tumor directly, but radium is effective tumor bone metastasis, and company explains radium alpha particle from radium break DNA. So of course, location is important, but it is not necessary. It is usually not necessary. Do you understand my meaning?
はい、わかりました。Okay, from the audience, you have other question? Either ask directly or typing in chat. if no questions, so before close this segment, I'm trying to make a summary from Ogawa Sensei presentation. First, astatin RGD peptide and iodine RGD peptide showed similar biodistribution and also alpha beta integrin specific tumor accumulation. And then the other summary is the similar biodistribution pattern among gallium DOTA RGD and gallium DOTA astatin RGD indicate that a radiotheranostics where gallium is combined with astatin should be applicable using molecular design with 2 labeling sites for metal and halogen. Well, ladies and gentlemen, now we have come to the end of the seminar. Thank you for your nice presentation, Sensei, and nice discussion. Thank you for taking time out for your busy schedule. 本当にありがとうございました。We finished our main. We finished our main segment. I will return this segment to MC today, Miss Ilma.
Okay, we would like to thank Dr. Phil Ratnadini Harini M.Pharm and Professor Kazuma Ogawa for bringing us to a very productive session today. So, ladies and gentlemen, we are currently in the closing session. We would like to remind you that the link to the attendance record form is now available and active. The link has been embedded in the chat column. Please fill out the form on the link carefully and completely to avoid identity writing errors on the certificate. On the same link, you will also be able to download your certificates later. Well, ladies and gentlemen, on behalf of the committee in charge, we would like to express our apologies for the mistakes we made during the event. Thank you for your active participation today and have a great rest of your day. See you later. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Waalaikumsalam warahmatullahi wabarakatuh. Sensei, お疲れ様です。
ありがとうございました。